So good morning. My name is Luca Mazzei. I'm from University College London, and this work that concerns the dynamics of polydispersed fluidized beds using DQMOM in this case, and focuses on the role of numerical diffusion, and has been done in collaboration with Paola Lettieri from University College London, who was my supervisor during my PhD, and Dr. Daniele Marchisio from the Polytechnic of Turin. So first of all, I'm going to speak a little bit just introduction to the generalized population balance equation. After, I'm going to introduce briefly the direct quadrature method of moment that we use to solve the population balance equation within computational fluid dynamics codes. After, I'm going to explain the experimental and numerical setup that we used for studying the mixing, and also we would like to study the segregation in fluidized beds using the QMOM and QMOM. And after, present the results and some conclusions and the future work. So in this case, what we did is we used, first of all, we introduced a number density function. This function characterizes the system of a polydispersed systems, where in particular we consider as internal coordinate, so the coordinate of interest, xi, which is the particle size, so the diameter of the particles. Also x is the position in space, and t is time. So we can also consider the diameter as the position in the particle space. We did not consider here the velocity of the particles as an internal coordinate, because in this first assumption here we assume that the velocity is a function of the diameter, or at least that there are equations that allow us to calculate the velocity once we know the diameter. So just to briefly summarize, if we multiply the number density function by dxi and dx, we have the number of particles whose size is in this differential range dxi, and in the volume dx, the differential volume in space. Usually we consider number density functions, but in this application we prefer to introduce a volume density function. This is just obtained by multiplying the number density function by the volume of the particles, which is a known function of the diameter anyway. The reason why we prefer to operate in terms of volume density function is because usually in fluidization we are more interested in volume fractions and not in number densities. So this is the only reason why we used this equation, this function. We introduced it. So at this point we can write the population balance equation in terms of volume density function, and considering only the particle size as internal coordinate. And so this is the expression of the generalized population balance equation, where as usual we have the accumulation term, the convection term in physical space, the diffusion term in physical space. We have the convection term in particle size space, we can say, and on the right hand side we have the collision integral, and the last term is just due to the fact that in this population balance equation we are using the volume density function and not the number density function. So in particular, as we will see in this presentation, the diffusion contribution plays an important role, as we will see later. So now our aim is to solve the population balance equation in order to calculate the volume density function. Nevertheless, and we would like to do this within CFD using a commercial CFD code. The problem is that this equation has more than 3 dimensions, so we have to come up with a numerical method in order to solve this equation within a customary CFD code. So how we solve this equation in DQMOM, in the direct quadrature method of moments, is like this. We presume a certain mathematical expression for the volume density function, which is a summation of Dirac functions. So this is basically the mathematical expression that we assume the volume density function has. From a physical point of view, this means that if we have a distributed population of particles distributed over the diameter, we assume that this population actually is made up of different sets of particles, Each set has a certain diameter, for example, Xc1, Xc2, and so on. And each set of particles with a certain diameter has a certain volume fraction, which is the weight of the quadrature, so phi1, phi2, and so on. And also the velocity, in this case, of each particle set, as I said, we assume that is a function, or at least is related to the diameter. So this is, from a physical point of view, what the quadrature approximation means. So how we proceed from here? We introduce the volume density function and this presumed mathematical function for the VDF in the population balance equation that I showed before. When we introduce the quadrature approximation of the VDF within the population balance equation, we come up with these two transport equations. The first transport equation is the transport equation for the quadrature weights, so for the volume fractions basically, and the second one is the transport equation for the nodes of the quadrature, that is for the particle sizes. As we see on the right hand side, we have some source terms for both equations. So now our aim is to solve these two equations within CFD in order to calculate the evolution of the quadrature nodes and weights. But first of all, before we can do that, we have to evaluate the two different source terms that we have here. So in order to evaluate the source terms, what we have to do is we have to force, sorry? Ah, yeah, it's turned off, but I don't know. It's off. Okay. Very sensitive. So in order to calculate the source terms, what we do is we force the VDF to satisfy, to predict correctly some moments of the volume density function. Now, the moments of the volume density function are defined here with respect to the size of the particles in terms of these integrals. So we force the VDF to satisfy some moments. And by doing this, by requiring this, we can calculate the source terms in the two transport equations that I showed before. So this is the way we calculate those source terms. Actually, in order to solve the fluid dynamic problems, we also need some transport equations for the momentum. Now, in general, this transport equation can also be derived from the population balance equation if we consider the velocity as an internal coordinate there. Since we didn't do this, in this model, in order to close the mathematical model, we use the transport equation from the granular, from the averaging, basically volume averaging, for example, and we close the moment equation for the momentum transport equation for the solid using the granular kinetic theory and Guidasbo's model. For the fluid as well, we use the equations obtained from volume averaging. And so basically the additional equations that we implemented are these: a mass conservation equation for the fluid, a linear momentum conservation for the fluid as well, and finally a linear momentum equation of conservation for each solid phase, for each quadrature class. Again, these are not obtained from the population balance equation in this model, but our aim will be also to obtain them by using the quadrature method. So now, how did we apply this model in order to study mixing and segregation? First of all, we consider two different classes of particles, of powders, sorry, a powder A and a powder B. Each powder has a certain particle size distribution. So powder A, we can say that as here are represented the particle size distributions, and we see powder A has a small mean diameter, and powder B has a bigger mean diameter. So what we did is we considered this fluidized bed, and we charged in the fluidized bed the two different powders, initially perfectly segregated. So with powder A, the small one on the bottom, and powder B on top. After, what we did to study mixing, for example, we supplied gas, air, in order to well mix the powders. After some time, we cut off the air, and we allowed the bed to settle down, and we checked if the bed was perfectly mixed or vigorously mixed. The way we did this is we divided the bed in many layers. We took the powder from each horizontal layer, and we sieved the powder. And after, we compared the different particle size distribution of each layer, and we checked that for each layer we obtained the same particle size distribution, which means that the bed was very well mixed. And our aim was to predict this evolution of the particle size distribution using the model that I presented before. So from a numerical point of view, what we did, we simulated, we implemented our model in Fluent using 2 dimensions. And in the quadrature approximation, as you saw before, we can consider as many particle classes as we want. So here in this first study, we consider the minimum particle classes, 2 particle classes. And the transport equations for the nodes and the weights of the quadrature were implemented within Fluent using user-defined subroutines. And in this case, obviously, since there is no chemical reaction and we did not consider breakage or agglomeration of the particles, is the simplest case possible just to start in this application. And for the drag, we considered the closure that I developed with Dr. Paola Lettieri recently. So the system is the one that the powders are the one that I presented. They are ballottini. So their density is 2,500 kilograms per meter cube. And as I said, we fluidized it using air. And the fluidization velocity that is here represented is high enough to vigorously mix the bed, the 2 powders. So now, before we can solve the model equations, so what we have to do is we have to find initial conditions for the weights and the nodes of the quadrature approximation. So for the phi's and for the x's. Now, in order to do that, what we did is this. We, from the experimental particle size distribution that I represented before, we can calculate the moments of interest of the particle size distributions. And from these moments, in this case, since we are using just 2 quadrature classes, we have 2 weights and two nodes, so we have 4 unknowns, so we need 4 moments. We calculated the first 4 integer moments of the distribution, and from these moments we back calculated the weights and the nodes of the quadrature using the Gordon algorithm. So by doing this, what we have is this. We have, for example, for powder A, this particle size distribution. From this particle size distribution, we calculated the moments. We back calculated the weights and the nodes. And so we have that when we use 2 quadrature classes, we can represent this powder using the 2 diameters they're represented and these 2 weights. So, for example, in this case, we said, okay, powder A can be represented as 2 sides, 75 and 103 microns, with these 2 relative weights. And the same we did for powder B. For powder B, again, we calculated the moments. From the moments, we back calculated the weights and the nodes, and this is the result. So once we have done this, we are able to initialize the mathematical problem. And so we have here the initialization in Fluent, where we have initialized there the weights of the quadrature, so the volume fractions, and here the sizes. So as we can see, the 2 powders are initially segregated. After we fluidize the bed, for 10 seconds in this case, and on the left-hand side we can see that we are mixing the powder vigorously, whereas on the right-hand side we see how the nodes of the quadrature, basically the sides, are evolving. After 10 seconds they have already evolved towards some constant values. So everywhere within the domain, the size now is the same. Initially, the bed was segregated and we had 2 different zones with 2 different sizes. Here, the 2 sizes have gone towards constant values. So now, the problem is, if in the population balance equation that I initially showed, we do not consider diffusion, so the diffusive term in physical space, we do not consider it, we have that the 2 sizes are 165 and 190 microns. Whereas if we consider diffusion, so we introduce the diffusive term in physical space, we have that the values are different, and in particular are 103 and 312 microns. So we understand that introducing that term plays an important role. After, when we cut off the air and we let the bed settle down, we see that on the left-hand side, we see the values of the weights of the quadrature, of the volume fractions, and we see that they are fairly constant within the bed, so we had a good mixing. And on the right-hand side, again, we have the values of the sizes, and these have not changed, are the same as before. Again, 165 and 190, or 103 and 312. So now, if what we can do now is to compare the values that we have obtained from the simulations with the values that we have obtained from the experiments. So if we consider so I said we divided the bed in many layers. For each layer we sieved the powder, and by sieving the powder we calculated the particle size distribution. So once we have the particle size distribution, we have the experimental particle size distribution. From this particle size distribution we can calculate the moments again and back calculate the weights and the quadrature. So on the left hand side we have the experimental values of the quadrature and the weights of the quadrature approximation. On the right hand side the predicted ones. If we do not consider diffusions, we see that the sizes are not well predicted, whereas when we introduce the diffusion we have a very good match between the two. So we understand the important role that in DQMOM the diffusion in physical space plays. So in future we would like to implement DQMOM using more quadrature approximation, because the more the quadrature the order of the quadrature approximation and the better is the approximation. We would like to study segregation. We started with mixing because it's simpler. And in this presentation I just spoke about DQMOM. QMOM is another method which is equivalent from a theoretical point of view, and we would like to implement it. Actually we have already in part done that. And after finally we would like also to include the velocity in the generalized population balance equation in order not to use the volume average equations of motion for the momentum. And with this I conclude my presentation.
Oh, I'm not sure what to do about the temperature for the different particles. You didn't present the energy equation, so I'm not sure how you close the problem there.
For now, we just use the results of the granular kinetic theory of Guidaspo, and we did not. We focused more on the rest. So for now, we didn't investigate in depth that aspect.
Because my point is that since you have different particles, you have different temperatures,
Yeah.
and not to emulate Charlie, but I think that Jim Jenkins, 25 years ago, did something with two particulates, and he was considering the equipartition of temperature. And I think that there is something there that you need to close when you have more than one particle. And I don't know how you choose the temperature.
Yeah, this is a problem actually, because no, I know. I mean,
theory relies on that, and all the
Yeah.
transport coefficients relies on that. So I think it's a very strong.
No, I think no. I agree with you. I also had a chance once to just mention this to Guidaspo himself, and he said that is a big problem. For now, we concentrate on the rest, but this is also very important. Yeah.
No. Just a remark to this, maybe you have to change the particle number density to a mass density. So that you multiply the number density with
By
the
the
mass, and then you get the right kinetic energy depending on particle size.
Okay.
And